This week's edition of New England Authors focuses on our climate with one of the nation's leading scholars, Raymond Bradley, who's written extensively and testified in front of Congress. Can we avoid climate meltdown? So, Raymond Bradley, welcome to the show.
Nice to
it's
be here.
Really good to have you here. You're a climatologist and distinguished professor of geoscience at UMass Amherst and research director of the Climate Systems Research Center. Your new book is Paleoclimatology, which is a very long word.
Yeah.
Explain it. What is that?
Paleoclimatology is study of how the climate has changed before we had measurements of thermometers and rain gauges and so on. So it relies on natural archives that have somehow stored information about the past climate. Most people will think of tree rings and the changes in the width of the rings.
Right.
But there are many other natural archives that tell us something about how the climate has changed in the past.
And one of those is ice cores, right?
Ice cores are one, for sure.
Yeah.
So if we go to polar regions and we drill down through the coldest part of the ice sheets where the snow has not melted, then that snow has accumulated over eons, and we can get a long record of how the climate in that part of the world has changed.
Now, this is the third edition of the book. What's been changing regarding research that you've come out with a new edition?
Well, I started this series in, I think, about 25 years ago, and the field was really just beginning then. And in the last few years, there have been a whole development of new instruments, very highly precise analytical instruments for studying climate in great detail in these archives, and new ways of dating material. New ideas about how the climate has changed, new ways of understanding what caused the climate to change. All of those things have required an update in the book.
Yeah. Now, you work on an era like 34 million years ago.
No, this book focuses just on the last 2 million years.
On the last 2 million years.
That's
right?
enough, actually.
Yeah. Now, we know that the climate way back when, in the Cretaceous period, in the dinosaur era, that was really hot, right?
Yeah, it was a different temperature.
What was it like at that time?
Well, it was from the geological records that we have. It was was more of a tropical regime. There were carbon dioxide levels in the atmosphere were much higher. It was a very different world at that time. And of course, you know, things have changed over time. And in the last 2 million years, we've had a series of ice ages and periods in between. So climate has fluctuated back and forth over time quite a lot.
Like the last ice age was about 15,000 years ago.
Yeah, probably a little bit beyond that. Maybe 20,000 was the coldest part of it, 25,000, something like that.
What was New England like during that time?
New England was buried under a large ice sheet.
A glacier.
And that ice sheet extended all the way down from Hudson's Bay all the way to Long Island. And the very edge of the ice sheet was marked by these so-called moraines, these rocky piles of debris that now form parts of Cape Cod and Long Island and other deposits that we find in the landscape.
How did humans do, like in Europe and Asia? How did humans do under those conditions?
There's evidence that people lived in Europe 30, 40,000 years ago. They must have been very hardy. They must have wore skins, presumably, and they ate a lot of meat. They hunted big animals. And they described their life and what they saw in these cave paintings that we see in parts of Spain and France and elsewhere.
Mm-hmm. So you use models as well. How does that work, computer models? Can you tell us that?
Yeah, so computer models are basically mathematical simulations of physical processes. So how does the atmosphere work? How does the ocean circulate? And just like weather forecast models, but we use them on longer timescales. So the models are run just like a weather forecast model would run, but instead of changes that we're interested on the timescale of hours or days, we're interested in changes that took place over tens of thousands of years, or at least decades and centuries.
Yeah, now you use so many methods, from insects to isotopes to ocean sediments and lake sediments, and we talked about the ice cores. Can you explain some of these techniques? They must be remarkable engineering feats.
Well, certainly there's a great deal of technology involved in recovering an ice core from Antarctica.
Yes.
The ice sheet is 4 kilometers thick. So you have to drill down and you have to keep the hole open using fluids so that otherwise the ice would just compress and you'd have your gear stuck. In the marine environment, there are big ships with so-called moon pools in the middle, which have like a hole in the middle of the ship where they have drilling rigs that can send coring equipment down to bring back sediments. And then on the smaller scale, there are similar kinds of drills, but much lighter, that are used on alpine ice caps in the tropics, for example, and in lakes to take sediments from the bottom of lakes. And then you go all the way up to very small drills that are used for drilling into corals or for taking tree cores from trees.
How does that work? What are you looking in corals?
So when you think about corals, the kind of corals that people study are not the sort of frilly, colorful corals that we often think of. They are big, massive domes of calcium carbonate that have been deposited close to the sea surface. And as the carbonate is deposited, it tells you something about the temperature of the ocean. And perhaps even the amount of rainfall that has diluted the salinity of the ocean at the surface.
So you've spent a lot of time in cold places, I see from your books. You know, you've been in the Arctic area studying. You almost didn't you almost get shipwrecked or something up there. So, and what was remarkable about me is about these ice cores is that they look for bubbles in them, right?
Yeah, so I don't do ice core research myself. I've been working on lake sediments, but those who study ice cores certainly can look for bubbles of gas or bubbles that represent samples of the atmosphere that have been buried along with the snow. And so if you drill a core down through the ice cap, you're basically going back in history. And you can get a history of what the atmosphere was like as that snow fell and didn't melt and was buried by more snow. And so you can extract the gas from these bubbles and look at what the composition was like over time, and then compare it with the present day. And when you do that, you find that the levels of greenhouse gases that we have today, like carbon dioxide and methane, are higher today than they've been for hundreds of thousands of years.
You're listening to New England Authors. Our guest is Ray Bradley, a climate scientist at UMass Amherst, and we're talking about the climate some time ago. Why do you study the climate some time ago? Why does it matter?
Well, let's step back. We've had measurements of temperature from thermometers for maybe a couple of hundred years in different places. And so we see this pattern of warming called global warming. And the question always came up when that was first shown to be the case. Well, how much of a cycle is this? Is this just something that comes and goes? What happened before the period when the instrumental records began? And so to do that, we needed to push back in time and try to put the present in a longer term perspective. And the other advantage, and when you do that, of course, you find that the recent warming is pretty unusual, and certainly no cycle about it. And the other part of that is if you can get a long record of climate, then you can understand perhaps what caused climate to change in the past. So for example, if we see there was a warm period in the past, we can try to figure out why was it warm. It certainly wasn't due to burning a fossil fuel like we see today.
Right.
So the question was, well, what other factors could have happened and caused it to be warm? And then by doing that, we begin to get a better understanding of what causes the climate system to tick.
Yeah, so what does cause that? Why does the carbon dioxide in the atmosphere increase and decrease?
What's happened in recent decades is we've added carbon dioxide to the atmosphere by the burning of fossil fuels. And so now we see that year-to-year variation, seasonal variation, but it's forced upward by the accumulation of fossil fuel from of carbon dioxide from the burning of fossil fuels.
Yeah.
And so that is something new. It began in the Industrial Revolution about the end of the 1700s, but it's got more and more acute over the last few years. In the last 50 years, in the last 35, 40 years, half of all the carbon dioxide from fossil fuels has gone into the atmosphere.
Yeah.
So it's really accelerated in recent years.
And the other half is taken up by the oceans. And
the oceans take up a lot of the carbon dioxide, and that causes another problem, which is acidification of the ocean. So the oceans are becoming more acidic as that carbon dioxide dissolves in the water.
Yeah. So I understand that the climate when Europeans were setting out to the New World was cold. Is that right?
It was colder than it is today, that's for sure. We sometimes call it the Little Ice Age. The
Little Ice Age.
Yeah.
What period did that last?
Well, it really began around the end of the 1200s, early 1300s, and it came to an end in the early 1800s, more or less. And it seems to be that during that interval, that 500 years or so, there were very many more big volcanic eruptions.
Oh, I see, yes.
And that put a lot of material in the atmosphere that reduced the incoming sunshine.
Yeah.
And that cooled off the temperatures.
So when we're on the subject of volcanoes, one of the solutions posed is to imitate a volcano by putting mostly sulfur into the atmosphere, sulfur particles into the atmosphere.
Yeah.
Is that a good idea?
No, not a good idea. Because we know, again, this is one of the reasons why we study paleoclimatology. We know that when that happened in the past, when we had big volcanic eruptions, there wasn't an equal distribution of impacts. So some parts of the world were much more badly impacted than others. For example, we think that there may have been changes in rainfall patterns, for example, in the Far East, in the monsoon regions of the world.
Yeah.
And so you can imagine, suppose some country decided, oh, we're going to control this global warming problem by spraying sulfate into the stratosphere, and then the monsoon regions of the world suffer.
Yeah.
There'd be tremendous repercussions from that.
Yeah.
So I think we have to be very careful about taking these large-scale so-called geoengineering solutions and trying to apply them when we don't have full understanding and full control of all the processes.
Yeah, that might be true, but I think that countries are going to do it. I think the things are going to get hot and people are going to get desperate.
Well, it may not be a country that does it. It might be Bill Gates or Jeff Bezos.
Oh, I see, yes. If I could get a little ahead of the story, are you pessimistic or optimistic?
I'm realistic, I would say. I'm a technological optimist. I think there are tremendous advances taking place in technology. I think every month I pick up Nature or Science journal and I read about clever people who are developing more and more efficient solar panels or better turbines for wind, renewable energy systems, new ways of transmitting and preserving electricity in batteries. all of that is happening at a frantic pace.
Yeah.
And so that's all good. Having said that, we've locked into the system already significant amount of warming, and that is not going to go away anytime soon. And in particular, the oceans have warmed and glaciers are melting, and so sea level will rise. And there's very little we can do about that at this point.
Yeah.
So certainly we have to adapt to the changes that are underway, but that doesn't mean those changes should be infinite. We can control them and kind of curb the negative aspects, perhaps, by controlling the emissions of greenhouse gases and switching to renewables.
Right. You're listening to New England Authors. If you're just joining us, we're talking with Ray Bradley, and he's a climatologist at UMass Amherst. And I want to turn to this very interesting little book you wrote. These are the two books that we have here are very scientific. This book here, called Global Warming and Political Intimidation, is a very personal book, right?
It was a cathartic experience to write that book.
Right. So you and a couple of other, 4 other scientists went before the U.S. Congress to give testimony.
So 2 of us, 2 others, 3 of us altogether.
Oh, 3 altogether, okay. You went to give testimony, and it was a good meeting that you had and testimony. And then later, they started challenging, a few senators started challenging you personally as a scientist, right?
Yeah, it's a little bit more complicated than that. But yeah, I testified in the Senate when John Kerry and McCain were chairing a Senate committee on global warming. And McCain certainly wanted to find out about what was going on. But at the same time, we had published some research that showed how temperatures had dramatically warmed in the last last century or so compared to the last 1,000 years.
Yeah.
Became known as the hockey stick.
Right.
Mike Mann, myself, and Malcolm Hughes were the 3 authors. This was a pretty innocuous paper scientifically. It was we were trying to see what we could say about the last 1,000 years using these different archives that I mentioned. And it became, in the eye of the public, a symbol of the problem that we faced. A very simple graph that showed this hockey stick shape. And for those people in the Congress who were very concerned not to have any pressure for legislation to control greenhouse gases, this became a real problem, and they wanted to destroy the credibility of this image. Yeah. And they chose to do so. They chose to do so by challenging the credibility of the 3 guys who produced it. And so they tried to. This was the House Committee on Energy and the House Committee on Investigations, and they wrote to us and demanded all copies of our emails, all of our research papers, contracts, and other financial records that we had. They just tried to make our life miserable, not with the goal of trying to understand how we arrived at the hockey stick, but with the goal of creating the impression that we had done something wrong. Yeah. This was compounded by Senator Inhofe in the Senate side, who asked the Department of Justice to indict 17 scientists for fraud, basically, for misuse of government funds in their research. And the basic premise of that was that the results that we came up with didn't agree with his preconceived ideas, and therefore we must have done something fraudulent with the taxpayers' money. Yeah. Thankfully, the Department of Justice did not take that up, But you can imagine all of this happening was very unnerving to three guys.
Yeah.
We had no idea where this was going to end. And fortunately, my university stepped up and helped me out with legal advice and told me what I should or shouldn't do.
Yeah.
And eventually, these were all Republican senators and congressmen, another Republican stepped up and said, "What on earth are you doing? Why are you harassing these people?" And he really made it a very public debate about this issue. And without his help, the name of him was Sherwood Bolett from New York, and he really put a stop to the whole thing.
Yeah.
He was chairman of the House Science Committee, and so he could see that this was not an attack just on the three of us, but more of a general attack on science in general.
Right.
And my university saw it that way too.
Yeah.
So
there was in the book. There's a hurt.
yeah,
A very strong hurt that you were personally attacked for being a scientist.
yeah, exactly.
Yeah.
And I think all of the major national and international scientific organizations came out with letters supporting us, saying that this was wrong, that Congress had no role in investigating, after all, what was simply a scientific paper published in peer-reviewed literature.
Right.
And they argued that it was the scientific community that had the responsibility to prove if it was right or wrong, not the Congress. And so at the time, when you're going through this, you don't realize what pressures you're feeling, and you don't know where it's going to end. So it was only after it was all over and I decided to sit down and write up what had happened that I really began to realize what an effect it had had on me.
Yeah. Yeah.
Because it was quite an open-ended inquiry. And they could have ruined us financially, and certainly our reputations are on the line.
Yeah. Yeah. So you've studied all this, the years, the last 2 million years.
Yeah.
And especially the last, since the Middle Ages and so on. What does that tell us about where we're heading now? Are we going to see 2 meter sea level rise?
Yeah, so the latest report that has just come out a few weeks ago has pulled together all the estimates of sea level rise, and the two problems are, one is that as the oceans get warmer, they expand in volume.
Right.
And the second is as glaciers melt and ice sheets melt, they return water to the ocean. And those are two unstoppable processes, really. And so one of the things that people don't really grasp is that when we put carbon dioxide into the atmosphere, it stays around for a long time. I mean, I'm talking centuries.
Right.
And so even if we simply stopped producing carbon dioxide tomorrow, the processes that we've already set in motion since the Industrial Revolution will continue for quite some time, because it takes a long time to remove carbon dioxide from the atmosphere.
Right.
So that means the consequences of the warming and the greenhouse gases that we've already put into the atmosphere are pretty much locked in already. So the best estimates now are that sea level will rise somewhere between 0.5 meter and 1 meter. It's sort of 18 inches to 3 feet by the end of this century around the world. And that's an enormous challenge, because you think about every big city that sits on the coast, Tokyo, London, San Francisco, Buenos Aires, etc.
Boston,
of course. Then each community is going to have to face up to what they can do about that, and it's not easy.
Yeah, and it's also not, we think of the ocean as a kind of a bathtub, but it's not like that.
No.
It rises differently in different parts of the ocean.
That's right. And ironically, we are more vulnerable here in New England to changes that may take place in Antarctica.
Right.
because the water will kind of swish away from Antarctica towards the northern hemisphere, and it piles up on the east coast of the U.S. So if there's a 1 meter rise in sea level here in Boston, it might be 1.1 or 1.2 meters. So 10 to 20% higher than the global average.
Yeah, yeah.
We see these images every year of houses getting washed away along the coast, and people say, "Oh, we're going to rebuild and or build a barrier or something."
Yes.
But it's not a good use of resources, to be honest.
Yeah, yeah, but it's not just the houses on the beach; it's tornadoes and hurricanes and things
Yes.
of wildfires and what's going on around the world, right?
So one of the things that exacerbates the sea level rise problem is the issue of more intense tropical storms. And as the oceans warm, they provide more heat that feeds into these hurricanes and tropical storms. And even this year we saw, I think, 2 Category 5 hurricanes in the Atlantic basin and 1 in the Pacific. So these storms are becoming more intense, and that piles up water along the coast. So you can have a 20-foot tidal surge, even if the hurricane doesn't, directly strike the land. And as these hurricanes sweep the ocean waters towards the coast. So you add a sea level rise on top of that, and it just makes it worse.
Well, thank you so much for being with us. It's not an easy topic, but you're one of the most eminent scientists in this field. This is New England Authors. We're here in Cambridge, Massachusetts. We thank the Curiosity Foundation for their support. We broadcast on stations throughout the region. You can watch episodes you haven't listened to on YouTube. And remember, watch locally. Thank you.